Yes, sir. Sir, please inform when you are ready at your end, we will start.
Sir, that's 1 second. Just give me a second.
Yes, sir. Take your own time. No issues. Dear participants, again, welcome back for this second session. Our guest and expert for this second session is Dr. SANJEEV KUBAKADDI. He is a owner of ITIE Knowledge Solutions Bangalore, and he will be taking 2 sessions with us. We are very much fortunate enough to have Dr. SANJEEV KUBAKADDI for providing his expertise in our area of recent trends and applications in the biomedical signal and image processing. In the first session, he will be talking on practical aspects of biomedical signal and image processing, as we had discussion with him during the finalization of the thing. And then probably he preferred that he will be taking some demos and then some cases as in the second session. I welcome you, sir. About Dr. SANJEEV KUBAKADDI, as I have told, he is the founder ITIE Knowledge Solutions Bangalore and mentor ITIE Academy. Am I getting? Yeah. He is entrepreneur with 16 plus years professional experience, with 10 plus years of experience in portable biomedical product development, and has interacted and worked with Fortune 500 companies. He is senior engineer in product development at Symphony Services Bangalore, senior software engineering R&D division at Convolution Solutions Chennai, and was research associate at Indian Institute of Technology, Delhi. His area of interest are image processing, digital signal processing, and he has got proficiency in algorithm development. He is interacting and working with universities and premier institutes for R&D activities. He was member of governing council of many reputed education institutions. Rather, he is member of governing council of many reputed education institutions, and he was ex-member of Board of Governance IIM Bodh Gaya, Executive Council member of VTU Belgavi, Academic Council member, Bangalore University, Skill Development Committee, Central University, Karnataka. He is a recipient of Mother Teresa Excellence Award 2013 presented by Integrated Council for Socio-Economic Development Progress, Kerala, and Rashtriya Udyog Ratna Award 2012 presented by Economic Development Forum, New Delhi. He has appeared in biography in Marico's Who's Who in World 2014. I have immense pleasure in welcoming him. Welcome, sir. With his expertise, I am very sure that participants will get insight in the field of biomedical signal and image processing. Sir, we have around 200 participants across the country for this FDP. Okay. And they are faculty members, research assistants working in various institutes, technical institutes across the country. And we are undertaking this 1 week online mode faculty development program under AICT Atal Academy, Government of India. Okay. Yeah. Now I am handing over to you and making you presenter, sir. You can start your session. Thank you.
Yes. So, a very good afternoon to one and all. I am very happy to be associated with the Atal Faculty Development Program. The topic that I am assigned is I need to speak on the aspects of biomedical signal and image processing. So I am able to see the screen. Anyone can run this.
Dr. Sanjeev sir,
I am sharing it. Yeah.
you can make your video on your report.
Video is not available on there. Yeah. Right. So ITI stands for Integrated Technologies for Industry and Education. We are into healthcare innovative products development. We have in-house developed as well as we have collaborated with many companies outside India. I'll just run through quickly just to give you a background from the healthcare perspective. We have designed world's lightest ECG patch. So, since you are aware about biomedical signal processing, you are aware how ECG is acquired. So this is a typical scenario wherein you will wear a lot of electrodes on the chest, right? It could be 3 lead, 6 lead or 12 lead. And if at all you wanted to monitor continuously for 24 hours, 48 hours, we call that solution as a Holter solution or Holter monitoring. It's a very, very painful job because this is the device which will be attached to the patient for 2 days, 3 days and so on. So you can see a device plugged to the body here. Okay, so replacing this, we have contributed to the design to the patch. So you can see here, this is the simplest patch. You just have to paste it and it has got a mobile hotspot. You can connect it to your mobile, smart mobile. So it will record, it will store and it will transmit continuously for 5 days. And what we have also done is we have built a AI-based algorithms in the backend so that if there is any abnormalities in the ECG, that will be detected automatically and there will be a alarm being sent to the cardiologist or to the family physician, wherever you can configure it. So we have given this patch to be configured to at least 5 people. So those 5 could be your cardiologist, 5 could be anyone could be your general physician or somebody at home who attends the aged one or people who have undergone the cardiac surgery and so on. So the design we have contributed in India in our office, and the product is registered in US FDA because of the certification, and it is already available in the market now. So we are selling this to the cardiologist. So basically, whatever pain, this is offline. There are a lot of cables that are lying on the body, which is an inconvenience to the patient, can be replaced with one simple patch. It's a gum-based patch. It sticks, so you can take a shower. But it is one time. It is not repeated as of now. So we have made it as a consumable so that people can use it and dispose it. So the battery has been tested for at least 10 days, but we claim that it should be used for 5 days. So another 5 days is a buffer. So on top of it, there is an AI algorithm, as I say. So these are all the opportunities available in the biomedical signal processing. So what goes into this AI is the algorithms. What goes into this patch is purely a semiconductor design. So that's one of the products, and this is a comparison of existing solutions. So this is the Holter monitor. You can see the size of it, and the dimension and the weight, okay, and you can see ours, and there are other products. So this is one product which we represent. The second one is we have collaborated with one more company in South Korea. This itself is a X-ray source. It is of a size of your camera, DLR cameras, and it exactly works like a camera. I'll show you a video shortly. So this is the lowest powered X-ray source, and it can be used for outdoor activities. We have been promoting this for the COVID-19 chest X-rays as well as the tuberculosis, which are two major things that are affecting the world even in this COVID times. So the tuberculosis patients are under a lot of stress because last 8 months they are not able to go to the X-ray centers because of the COVID patients. And COVID can also be detected from the chest infection as well. So it just takes 3 seconds to take one X-ray. And this is the reflector, whatever white color you see or the black color you see, this is the wireless reflector. So we have working with the smart clock as well. So we call it as a smart heating solution. So once you heat it, so this can be kept under your jerkin so that it will maintain the body temperature. So this we are promoting to the defense where the Siachen kind of areas. So it's going on. So this is how you can wear it. So it will maintain the temperature of whatever you set it. So this is another product which we have worked with. It's called the connected healthcare kit. So it has got a multiple parameters. So it has got a blood pressure, it has got a SpO2, it has got a ECG, it has got a temperature, it has got your glucose monitoring. So all fitted into the small suitcase. And what we did is we developed a EMR software fitted into this tab, which you can see here. So this fitting will be done here. So as soon as you measure all these biological parameters, it will get displayed here. And also we have written algorithms to detect any abnormalities. So this is how the parameters will get displayed: the temperature, the pulse rate, the oximetry. As you are aware, these 3 parameters are widely measured in the last 6 to 7 months because of the COVID. So the oximetry, that is the SpO2, and then the temperature are being monitored, regularly for the patients who are affected with the virus. So this is a handy suitcase. So the weight of this is less than 3 kg, so that ASHA worker or any medical practitioners, they can take door to door and then do the monitoring, or we are proposing it for the primary healthcare centers and so on. So this is a brief product. So you can visit us at itie.in for other products. I'll talk about the other products as and when we move on. So when it comes to biomedical signal and image processing, what we strongly believe as a product developer, as an algorithm developer, as a researcher, is the fundamentals. Once we are strong on the fundamentals, any problem that we take up can be divided or splitted into the fundamental understanding. I keep interacting with a lot of researchers. The only problem that I find with the researchers currently is their fundamentals are still shaky. Then the question comes, what kind of fundamentals that are required to really build a signal processing or medical image processing algorithms or a software or even for that matter the hardware. I have listed few concepts and I would like to talk about it quickly. These are the fundamentals which we have studied. We keep on discussing this, but unfortunately the physical interpretation of these concepts, the physical interpretation of these concepts is required, that is our personal experience. For example, let's say frequency. I am very sure as you are a faculties and you have been teaching signals and systems, signal processing, image processing, video processing, or communication systems, etc. You have come across frequency from a quite long time. But what is there to understand in a frequency? So whenever I ask a question, what is a frequency? The standard answer that I get from most of the people is, frequency is nothing but number of cycles per second. Frequency is nothing but 1 over t, that is the inverse of a period. It is nothing but a repetition per second. These are the three standards that we get. But if we really want to understand what is the physical interpretation of a frequency, why should I know the frequency in a biomedical signal? Why should I look for a frequency in an image? That requires an answer. Just to make you understand what is a contextual understanding, I'll just take you through a couple of questions, and then since this is a one way, I will ask the question and I will answer it for time being. You are listening to me and you would have also listened to the cricket commentary yesterday. You are listening to me, you would have also listened to the cricket commentary yesterday. There is a characteristic difference between my speech and the speech that you would have heard yesterday. I am explaining you a concept. Somebody explained you what is happening in the cricket ground. That's it. They spoke yesterday. I am speaking to you today. There is a speech signal and what you are hearing is also a speech signal. But there is a characteristic difference. That characteristic difference is the rate at which the words are being produced. Meaning, in the cricket commentary, what you heard yesterday, the rate of change of words is fast. In my case, the rate of change of words is slow. Obviously, there is an advantage with my signal. What is the advantage? The greatest advantage my signal has is you are able to hear each and every word I am spelling it out. You are able to hear each and every word I am spelling it out. The reason being the rate of change. Hence, you have the maximum information coming out of my signal. What happens in case of a cricket commentary? I am not talking about English. I am not talking about pronunciation. I am only talking from the rate of change perspective. The rate of change is faster, and by the time I or you understand one sentence, we would have already missed a word or two in a sentence. By the time a second sentence would have already started there. So, a slowly changing signal carries maximum information of interest to you. If somebody talks a lot, we always call them as a high frequency guys. You would never have heard anybody calling anybody as a low frequency guys. No. You would have heard or you would have called somebody who talks a lot always as a high frequency guys, overhead transmission, something like that. So these are all the derived from our day-to-day life. So what did we really mean? What we meant was whatever he, she is speaking is all noise, no information is what we meant. So that is how we classify the people. At home, you would have noticed babies going to the sleep, listening to the lullaby of whatever mother sings. Does this mean that all the mothers are a great singer? That may not be the true. However, each and every baby goes to the sleep listening to the lullaby sung by a mother. Then there should be a characteristic in that. That characteristic has something to do with the frequency. The rate of change, we call it as a melodious. We call it as a soothing. We call it as a slowly changing phenomenon. Makes the baby sleep. It is not that a mother is a great singer. No. However, what makes babies going to the sleep is the frequency, is the soothing effect, is the slowly changing phenomenon that we create. If we have a habit of listening to the old songs, let's say Mukesh or Muhammad Rafi, before going to the bed, typically if you don't get a sleep, we all have a habit of listening to the old songs. There is a characteristic in those songs. The characteristic is again frequency. Many a times you don't realize when you slept. So there is a characteristic. So I can take n number of examples. For example, the FDP is named by the former Prime Minister of India, Sri Atal Bihari Vajpayee. If any of you have heard his speech, that was the slowest signal that you can think of. He used to spell a word after so many seconds of delay, and each word carried more meaning than a paragraph of what I am speaking. So that was the slowest signal example. So by frequency, what we understand the rate of change. What do we understand by the rate of change? By rate of change, we understand is it a slowly changing phenomenon or is it a fast changing phenomenon? If it is a slowly changing phenomenon, it is of interest to us. All your biological signals, they all fall in the low frequency. For example, your ECG, it will not be more than 100 Hertz. It is not in kilohertz or megahertz. It is in Hertz. 0 to 100 Hertz is what we claim the maximum. For example, EEG, it is 0 to 200 theoretically. But practically, we always fix it between 0 to 60 Hertz for analysis. Then, it signifies that all your biological signals are of low frequencies. And hence, there is every potential that the signal will be lost when you are recording it from the real world, because there may be other dominating frequencies in the real world which gets mixed up or which gets added up to your biological signals. So, analyzing a biological signal essentially requires, if at all you are measuring it from the real world, when you are measuring it from the real world, you need to make sure that any signal which is more than 100 Hertz, hypothetically, you should eliminate it. The moment you take out any signal that has come into your system through the data acquisition system, which is having more than 100 Hertz component, I am not interested in analyzing because it is not my biological signal. Then you are narrowing down your acquired signal frequencies to 0 to 100, and then you can go further on. So the first concept that is required in understanding a biological signal or even a medical image processing perspective is the frequency. I will repeat. Frequency gives you the rate of change. Thereby, you understand, is it a slowly changing signal or is it a fast changing signal? If it is a slowly changing signal, that is of interest to you. We did not call all the high frequencies as useless. No, we did not say. But our primary interest lies in understanding a slowly changing signal because it carries information of interest to us. So, this is one concept. Like this, you can extend this to the two-dimensional data. X equal to f of t, x equal to f of t, the one-dimensional signal where x is a function of an independent variable t. So if it becomes a two-dimensional, then you call it as an image, you call it as a space, you call it as a xy coordinate. Any value in the xy coordinate, you call it as a intensity value, you call it as a pixel value, and so on. So when I try to analyze the image, you are trying to understand whether there is any change happening from one pixel to the next pixel to the next pixel to the next pixel to the next pixel. If it is a slowly changing phenomenon, it has to be a low frequency image. Wherever you have an edge, curve, line, a sharpness, or a noise induced in an image, then the rate of change of intensity values will abruptly change. For example, hypothetically, if you take the first intensity value as 10, and if I am focusing on this part of the white screen with my camera, and if I capture the image, the intensity values will be more or less similar. It may be 10, 10, 9, 8, 8, whatever it is. We are not calling it as a low frequency image because the values are low, like 10, 8, 9. No, we are not calling it as a low frequency because of this. We are calling it as a low frequency image because when you go from one pixel to the next pixel to the next pixel to the next pixel, the change is a slow change. If it is a slow change, it has to be a background or it has to be a low frequency information in an image. Let's say suddenly a line comes or a curve comes or my face comes, etc. Then there will be a sudden transition. So when I am talking to you, I can also increase, I can cough, I can whistle, or somebody may put a horn outside this building. So all that comes as a sudden change compared to my speech signal. So hence we classify those signals as noise. Okay. So that's about frequency. Then the signals and systems. Signal, the mathematical way of representing it is a function of some independent variables. You classify a signal as a causal signal, non-causal signal, linear signal, non-linear signal, linear time invariant, linear time variant, even, odd, blah, blah, blah. There are different types of signals. Similarly, for a system, anything that you see around is a system. For example, wherever you are sitting, there may be a fan, there may be a AC, there may be a computer, there may be a phone. All of these dealt by us as systems. What does it mean? For example, I am an electronics engineer, and if you ask me what goes into my mobile, I don't know. What I know about the mobile is the input I provide to the system and the output I get out of the system is what is known to me. What is happening inside the signaling and all is not known to me. So it is like a black box to me. Same as with your fan. For example, if you have a standing fan next to you, what is your understanding about that fan? Do you know what kind of a motor is inside? How many rotors are there? How many stators are there? What is the wiring type? Absolutely, we don't know. But we are using that fan. How are we using that fan? We are using it because we have got certain understanding about that fan. What is that understanding? The understanding what I have about the fan is, if I press button number 1, it is going to give me a low speed. Let us say 600 rotations per minute. If I press button number 2, 800 rotations per minute, hypothetically. If I press button number 3, maybe 1000 rotations per minute. So my understanding about the fan is, the input I provide to the system and the response that comes out of the system is known to me. I don't know what kind of a motor is sitting, how many rotors are there, how many stators are there, what is the wiring type. Absolutely, it's a black box to me. I only know the fan in terms of its input and output relationship. Same as your digital filter. What is a digital filter? A digital filter is a system. What it does? Whatever noisy biological signals or whatever noisy image that you have, you pass it on to the filter. What happens? Whatever comes out of the filter is a filtered data. So how did you design that box? You designed that box based on your requirement. What would be your requirement? Your requirement could be to eliminate the power line noise interference. Hence, that box should be designed such a way that it passes 0 to, let us say, 49 Hertz and 51 Hertz to whatever it is, it will pass. So what it essentially blocks? It essentially blocks a frequency component of 49 Hertz to 50 Hertz. That's hypothetical. So that becomes a notch filter or a band stop filter. You are stopping a particular band of frequencies. So you design a box such a way that it blocks a range of frequencies. It becomes a notch filter. Or you only wanted to pass certain range of frequencies, fine, you design it. So, your digital filter will not be different than the fan. Your digital filter will not be different than your phone. My understanding about the digital filter would be, given an input, get an output, find out the relationship between the output and input. That is what it is. So, there are different types of filters, filter design process, etc. So, I will not get into that, but that knowledge is required. Okay, so then the ADC process, though it is very fundamental concept, it is required to understand how do we digitize the analog signal or what are the advantages, disadvantages of analog signal processing or the digital signal processing. So ADC plays a very vital role in biomedical signal processing especially. So the ADC, the bit width, that is 2 to the power n, so that n decides what is the resolution with which you wanted to record the signal. So most of the biological signals, 8-bit resolution is more than sufficient to represent them. Then the convolution and correlations. Convolution is a mother of all the algorithms. Most of the things that you see today in the signal and image processing are a contribution from the convolution algorithm. Very powerful algorithm. Immediately after convolution, Laplace derived Laplace transform. For example, in the convolution equation, if you are able to recollect, y of t equal to x of t convolved with h of t. where x of t and h of t are a continuous signal. Y of t is also continuous. So this convolution symbol you replace with the integral. Then y of t equal to integral tau going from 0 to infinity or tau going from minus infinity to plus infinity, x of tau into h of t minus tau into d tau. So what it says? It says one signal is kept as it is, another signal is time shifted. A time shifted signal is multiplied, then added. So shift, multiply, add is what you have studied as a convolution. It is not so simple. Though mathematically it is shifting, multiplication, addition, integral if it is continuous, summation if it is a discrete one. So the discrete convolution you would have written as y of n equal to summation k going from 0 to infinity x of k into h of n minus k. So what we do? H, you are doing a time shifting, you are multiplying with x, you are doing a summation. Then this h of n minus k becomes very, very crucial from the signal and image processing. This h of n minus k or h of k or h of n is termed as a impulse response of a filter or impulse response of a system. So what is the impulse response of a system? Impulse response of a system is the response of a system for an impulse input is termed as an impulse response of a system. So that is very, very crucial. It is like a reference. For example, you don't know who I am to begin with, and I also don't know who you are. So if at all you wanted to characterize me, I am an unknown system to you. You don't know what kind of a system I am. Am I a knowledgeable system? You don't know. Am I a polite system? You don't know. Am I a moody system? You don't know. I am a system is what you know. What I know about you is you are a signal. So what will happen when an unknown signal like you talk to an unknown system like me? You cannot predict what will come out as a response. I may respond to you politely, I may not respond to you, I may over-respond, I may under-respond, I may respond to rudely. So I have n number of behavior that I can exhibit. So in order to characterize me, what we typically do, so we do this analysis in day to day. For example, typically if your faculties, HODs or principals, the students are very, very intelligent signals. Whenever they wanted to meet you, so they will not come directly. They will send a student who is very, very pet to you. So that they wanted to find out your mood, they wanted to find out your status of mind. Only if you respond politely, if you are in a joyous mood, then the others will come. Otherwise, they will simply put that standard signals for text. So they know how to test a system. So they will not come directly and talk to you. So they try to characterize by sending a favorite student in the class to the teachers. So based on their interactions, then these unknown signals will come. So it is like giving an impulse to an unknown system to characterize it with impulse response of the system. So we represent it with h of 0, h of 1, h of 2 and so on. So that is the convolution. Transforms plays a very, very vital role. Transforms have enabled signal and image processing quite possible today. Whenever we ask what is a transform, the standard answer that we get is converting from one domain to another domain. It is not. It is not a conversion. Transformation is a process of mapping from one domain to another domain. It is a mapping. It is not conversion. Why do you want it to map from time domain to frequency domain? There is a limited understanding of a signal or an image in one domain. For example, I am a signal, I am a system, and I exist in Bangalore. Bangalore is a time domain for me. As long as you analyze me in the time domain, in the Bangalore domain, there are certain characteristics I exhibit. What do I exhibit? I am a very, very confident signal. So I exhibit a character called as a confidence. So I am a highly confident signal in Bangalore because this is the domain where I exist. I know people, I know the local language, I know the areas. So my confidence level is obviously high. What happens if I go to an unknown place? Let's say you take me to a very, very remote place where the language is not known. Let's say you take me to the border, or the remote areas in Orissa, where the local language is the Oriya. My confidence will obviously change there. My confidence will not be as exhibited in Bangalore for certain. So if you analyze only in Bangalore, you will have a limited understanding about me, saying that, oh, this signal is confident. That may not be true. So whenever you see a signal in the time domain or an image in the spatial domain, yes, there is a lot to understand, but that understanding is not complete. It's a limited. So what do? We need to map. Why do you want to map? You wanted to map because there is one characteristic of the transform, whether it is a Laplace transform, Fourier transform, Z transform, DCT, wavelet, whatever transforms that you have come across so far, all these transforms have got a characteristic of segregating the frequency of a time domain signal. What does it mean? Now I am talking to you. I have got certain frequencies being produced. Let us say hypothetically, my signal frequency is 70 Hertz. So when you record my speech signal now, it is not just 70 Hertz which is visible. I am using a standalone machine here which is making a lot of noise. I am sitting adjacent to the windows where there are a lot of vehicle movements, horn, etc. When you record my speech signal in the real time, all the other signals are also getting added. So when you really check the effective of it, what you get a representation at 70 Hertz, maybe 100 Hertz, maybe 150 Hertz, maybe 1000 Hertz. Based on my understanding about a signal or image processing or a frequency, I know that 70 Hertz corresponds to the speech. Rest all, I am not interested. But if you see the signal in the time domain, it is very, very difficult to differentiate which is a signal, which is a noise. Which is a signal of interest to you, which is a signal that is not of interest to you. It is very, very difficult. So, we try to make the understanding simpler by exploiting the uses of these transforms. Transformation is not to simply map. In the process of mapping, what exactly happens is a segregation of frequencies. And we have got an understanding about frequency, what is of interest to us, what is not of interest to us. Hence, transformations or the transforms plays a very, very vital role. So, Fourier was a student of Laplace. When Laplace was there, it was only continuous signal processing. Hence, you have a continuous Laplace transform. There is nothing like a discrete Laplace transform. So what Fourier did, Fourier was working in the same laboratory. So what he did was he continued his research and then he changed the basis functions from e to the power minus st to e to the power minus j omega t. He redefined the basis functions and he derived both continuous Fourier transform as well as discrete Fourier transform. So both we would have studied in the signal processing, and they are very, very crucial. And if you are dealing with image processing, you would have come across a DCT, stands for discrete cosine transform. So what happens in case of Fourier transform, this e to the power minus j omega t can be expressed in terms of cos of omega t minus j sin omega t. So we are not comfortable with this minus j sin omega t because it's a complex. So if you eliminate the imaginary from this complex number, what you are left out with is cos of j omega t. Hence it is called as a discrete cosine transform, widely used in all the commercial compression algorithms starting from MT3, JPEG, MPEG-1, MPEG-2, even in MPEG-4. Okay, so DCT is a default transform that is being used. Then comes the digital filters. So what you need to understand in the digital filters is the digital filtering is nothing but a convolution. Convolution between what? Convolution between the input signal, let's say f of t, where the impulse response of a filter h of t. So if you simply convolve, that process itself is a digital filtering process. So what is your job? Your job is to design H. H will not be given to you. In order to design H, there is a process in the filter design. There are different types of filters. It could be frequency based, it could be phase based, it could be shape based, moving average window, etc. There are different types of filters. So what you need to remember is the digital filtering is nothing but the convolution. So let me move on to the medical imaging quickly. So most of these images are obtained from the rays, the radiations. So in the initial presentation I showed you one of our products, the portable digital X-ray, that is of a size of a camera. You would have seen the X-ray machines of room size. So my X-ray device is highly portable. So wherever you are sitting, I can take your X-ray. I'll just show you one small video. Okay. So hope so it will just take 3 seconds to get one X-ray done, and this is the reflector, whatever that fellow is holding, and what I am holding here is the X-ray source. So you can see the chest X-ray onto the screen, and you can do all the image processing. We have integrated all the image processing algorithms here. So this is one small product. So how a medical image is obtained. So this is an X-ray. You can take an X-ray of a chest, neck, ankle, palm, knee, whatever it is. So this is world's safest X-ray, and we have contributed to the algorithms, and it is still ongoing. So the AIs are being implemented. This product has been appreciated by World Health Organization recently, couple of months back. So they have also tweeted from their official Twitter ID, mentioning our company name, our product name, and my name individually, saying that this product is a game changer in the tuberculosis and COVID. So we have been working with the government. So basically the medical images are all obtained by different radiations. It could be X-ray, it could be MRI, it could be CT, whatever it is. So I'll not get into this image formation and all. So these are the sample X-ray images of a dental, a chest, or of palm, and so on. So this is a 4D fetal profile using the ultrasonic scanning. So these days, after 6th, 7th month onwards, we'll be able to see the exact space and the development of hand, leg, etc. of the fetus. So that's a 4D ultrasonic scanning that you can see here. So there is a great work that has happened on the instrumentation side. There is lots to be done on the processing side. So what we are focusing here is the processing. So our focus is not to design these devices in this workshop. So that requires a hardware different understanding. But whatever images that we get from all of these devices, our job is to do analysis. So you may get into a research area of chest X-ray analysis, automatic pneumonia detection, automatic COVID detection, automatic tuberculosis detection. It could be dental X-ray analysis. It could be osteoarthritis, where my research is into. So we can go for an early detection of any of these problems. So these are all open-end problems and ongoing research works. So typically, the acquisition part is what we start. Okay, so it involves your X-ray, it involves your MRI, CT, whatever it is, and this is what you are discussing it. So the previous speaker, I just logged in early for 5-10 minutes, so I was able to see he was talking about histogram, etc., etc. But I wanted to highlight the point that as a researcher, what is required out of you is not a great algorithms, is not an advanced, there is nothing like advanced concepts. I firmly believe for the last 15 years, we have been working on the biomedical signals left, right, and medical images left, right. What we fundamentally believe is only the fundamental algorithms have to be strong. Anything else that you can think of is built on this fundamental understanding. There is nothing like an advanced concept. So for example, the pre-processing. So you have heard pre-processing a lot. So why pre-processing is required? I need to know. Pre-processing is required because as and when you record an image or a signal, there are other unwanted signals which will embed into the signal of interest. Hence, before you wanted to analyze your signal, those unwanted signals, what you call them as a noise, should be eliminated. Fine. So how do I eliminate it? Do a pre-processing. So what does a pre-processing involve? Pre-processing essentially involves a low-pass filtering. So what will a low-pass filtering do? A low-pass filtering will only pass low frequency and it will stop all the high frequencies. So all the high frequencies which we classify them as a noise will get eliminated in the first stage. Fine. Once pre-processing is done, get into what you wanted to do in the image. For example, you wanted to detect a tumor in an image. Fine. Detection of a tumor is the fundamental problem statement. What do you mean by detecting a tumor in an image? You just have to scan it. Check whether there is a slow change or a fast change. Wherever there is a tumor, wherever there is a dead cell, it will be differentiated from the healthy cells. So when you scan the healthy cells from left to right, let's say, not much change, not much change, not much change. So no change, no change, slow change, small change, etc., etc. So wherever you have a tumor, there will be a sudden change. Fine, detect it as a abnormality. Then you wanted to take that out. So segmentation is nothing but dividing into many segments. Fine, you segment that tumor into separate things. Then you can compute what is the size of it, what is the volume of it, etc., etc. That's what is analysis, and then finally diagnose what is the outcome of the processing. So these are the broader steps. So typically pre-processing involves filtering, detection involves identifying edges, etc., etc. You can delimit the object, that is a segmentation. Okay, so you can compute volume, curvature, or mean values, or even the statistical values, etc., etc. Then it gets into the classification mode. So this is the original image, and this is a enhanced image. You can find out the local objects as well. So if at all you wanted to detect something, so it has been marked there. Okay. So I'll just share this. Okay. So the classifications is the last stage, because most of you might be working on classifiers or automatic classification of the data into normal and abnormal. So there are different linear, non-linear classifiers that you would have come across, KNN, SVM, which are being widely used, or it could be even artificial intelligence, ANN algorithms. So they will be able to classify is it a normal or abnormal. So in the afternoon we will have a live demo wherein we, based on our concentration level, we would like to show you how a robocar can be controlled. It's not a recorded one, it's a live one. So we have set the threshold value. Once the concentration level is high, the car goes. The moment concentration drops, car stops. So that live example also will show you maybe 2 or 3 examples. So typically the discussions evolved around this. This is what we call it as a contextual understanding. So we firmly believe that these fundamentals, I will take the questions maybe once we just complete this. Just 2-3 minutes I will take all these questions. So we firmly believe that your research work should be built on these fundamentals. These are the only fundamentals that you should be good at. There is no other algorithm that comes in your way, provided you have understood them thoroughly. Meaning you should go at a very, very lowest possible way. For example, at samples, if it is one-dimensional, at pixel level, if it is two-dimensional. So what exactly is happening at a sample level? What exactly is happening at a pixel level? If you are able to capture that, then there is nothing like that. So in a nutshell, the biomedical signal processing involves the data acquisition. So in the data acquisition, we have a ECG machine, we have a EEG machine, we have a EMG machine. We also designed and developed and supplied to Indian Air Force a multi-parameter device. It's there, it's available on our website. It's called Biomedical. So Indian Air Force wanted us to develop multi-parameters in a single device, a portable device. It's of the size of a mobile. So what we did in that, we had ECG, we had EMG, we had SpO2, and then we have respiration rate, all fitted into a single mobile sized device, and that device was put onto the pilot. and they used to test their fatigueness and then other biological parameters when the pilot goes vertically up or when he's flying against the gravitational force like 3G, 4G, 5G. So it is so that is the application we developed for Indian Air Force. So what it involves was it involved multi-parameters to fit it into that. Once you have a RAS signal, then it begins with pre-processing, filtering, or even the classifying whether is it a normal or abnormal. So that is a kind of a block diagram that you would have seen for the biological signal processing. Same thing is also valid for medical image processing. So you don't have to worry about the devices these days. You can only focus on the analysis. So your domain lies in the analysis side. The device, making the device is our headache, like people like us who are in the industry who develop these devices. So that's the in a nutshell introduction to signal and image processing. So let me see here is. Could you please suggest problem statement for diabetic retinopathy? Okay. So there are a lot of papers available for the diabetic retinopathy. Maybe I have one paper I can share on the screen. Okay. There's the video. Okay. So you can search diabetic retinopathy. So one of the early paper that you will find in our name, you can just Google with this keyword. So we were able to automatically classify we were able to detect the cup size, cup to disc ratio, and then the blood vessels, etc. So that paper is also available. So I can share that paper in the PDF file. Okay. So okay, then great to listen. Okay. So I will be happy to take any questions because this is a very, very generic topic, but day in, day out, we work on the biomedical signal and image processing applications. So you can visit us at I have just given in the chat ID, the website, where you will get to know the research area, the papers, as well as the product. So if your interest lies in the biomedical instrumentation, also you can get in touch. Analysis also you can get in touch with us. Okay. So any other questions? Yeah, participants can put up their questions. The participants can put up their questions in chat box or maybe in question answer tab. I look for the question. Okay, so my name is typed wrongly yesterday, so I'm just typing it correctly so that if you Google it, you should be able to get it. So it's KUBAKADDI, Sanjeev KUBAKADDI. So, okay. Yeah. So, yeah, sir, please continue. There was one question which is in the chat box. Is there any scope for hyperspectral image processing in biomedical image processing? Where is it, sir? In chat box. 1 second. It is to host only. Oh, it is to host. Okay.
Yeah.
What is the question?
I will read it out.
Yes.
Is there any scope for hyperspectral image processing in biomedical image processing?
Of course, yes. See, the research areas are getting into kind of a hybrid. So earlier it used to be a isolated research or a discrete research, but now what is happening is it's like a hybrid research. So the answer is yes. So the multispectral image processing is yes, it is being exposed, and if you think of a fMRI, people have already started working on it. So that's a good area to work on. Only thing is make sure that you get the images that are required for you, the inputs that is required for you is in hand. So otherwise, if you start the research topic and if you find it difficult to manage the data, then research will not head anywhere. So better make sure that you tie up with some industry, you tie up with some institutions where the data acquisition is possible there. So because every institution cannot have that costlier data acquisition systems, but at least collaborate with people who have such devices. So answer is yes. So you can get into multispectral learning.
Sir, another question is there.
Yeah.
Which is the better method to convert 1D signal to image?
No, there is nothing like a method. Okay, so for example, the algorithms like the transforms like DCT and all, so they have given the zigzag scanning as mapping from 1D to 2D. But there are a lot of work that is happening from 2D to 3D. So wherein we did one work on mapping from 2D to 3D. That's also available online in the JOMB magazine. So there is nothing like a standard algorithm for mapping from 1D to 2D. So you can find out the latest algorithm. So far what is being used is the zigzag scanning to convert it from 1D to 2D.
Yeah. Thank you, sir. Using imaging, I am facing many problems in collecting data sets. Yeah, sir, I will read it out again. Yeah. Cardiovascular diseases using imaging. That is the area that particular participant is willing to ask a question or has asked a question. He is facing or he or she is facing many problems in collecting data sets. Okay. Where can I find the data set? Is there any special source for it?
See, that is the thing that I in fact answered just before now. Data is everything. Data is money. Data is crucial. Before you pick up any topic, make sure that you zero in on the data. So as far as this specific question goes, the cardiovascular, I don't see there is any standard data set that is available. So you need to work with any cardiology centers in your place. You have to tie up with a hospital or a doctor. You have to associate. And data collection is a pain because we have gone through this stage. And in fact, our first product, what we brought for biomedical signals was that only. So we wanted to reduce researchers' time. So we designed the biomedical signal data acquisition system so that others don't waste their time in collecting data. So it is just plug and start. So as far as this cardiovascular question goes, you need to work with local centers, and you need to have official MOU so that in the papers you can mention their name or you can acknowledge their name. So that, and then there is ethical clearance from your ethical committee. as well. So this has to be done locally. So there is no global standard, I believe. Which is more efficient for MRI image enhancement, spatial domain or frequency domain? That is another question by Professor Radhika. See, there is no hard thumb rule whether the spatial domain is good or frequency domain is good. If you really understand what is a spatial domain and what is a frequency domain, this question will not come. Let me simply put it. Spatial domain gives you the statistical understanding of the data. For example, you can find out the statistical parameters. But in the spatial domain, you don't understand what is the frequency. And also, if you understand the convolution algorithm thoroughly, convolution algorithm says a convolution in time domain is a simple multiplication in the frequency domain. Whatever shifting, multiplication, additions that we are supposed to do in the spatial domain becomes a simple multiplication of the spectrum of an image, spectrum of a filter will give you the spectrum of the filtered image. So typically, as far as the computational goes, frequency domain filtering is easier. As far as the computational goes, frequency domain filtering is easier as well as it is efficient, because what we do, in order to go to the frequency domain, we apply a Fourier transform on the image, we apply a Fourier transform on the filter, we simply multiply the spectrums in the frequency domain, then we apply inverse Fourier transform to get it to f of x comma y form. So it is not, in that way, frequency domain is efficient as far as the filtering is considered. However, you require both the domain analysis for your image processing to be complete.
Yeah. Thank you, sir. We'll take one more question which is on the panel. It goes like this. Is there any method to transform a thermal image to normal digital image?
See, these days, the thermal scanners or the thermal cameras that you might be using, they will have an option to store the data in the digital form. So, format could be anything. So, you don't require third-party converters to do that. I believe the thermal cameras, what I have seen, so they will allow you to store it in the digital form directly.
Yeah. Thank you very much, sir.
Yes, sir. So, if my video is compressed, how can I retrieve more information? See, the compression is to reduce the file size. The compression was achieved to reduce the bandwidth. So these are the two reasons with which compression algorithms came into picture. So MPEG-1, MPEG-2, MPEG-4, or if it is ITU standards like H.263, H.264, and so on. All of them have what? Certain limitations. Meaning, the compression, the whole idea of compression is possible only because we assume that there is a redundant data in the video. What could be the redundant data? Just a hypothetical question. The redundant data, for example, your eye, whenever you are watching a TV, you are not sure that in 1 second, 25 images have come and gone, because your eye is insensitive to the change that is happening. So what did they exploit? They exploited saying that, okay, more than 25 frames per second is a redundant data. Okay, let us restrict on to 25 frames per second or 30 frames per second if it is NTSC or PAL standards. So, this MP4 is already compressed. Okay. So, in order to read that data, you require a MP4 decoder. Okay. So, whenever you see a file in the form of a .mp4, it is already compressed and it is placed in the server, let us say. If at all you wanted to decompress it, what you require is a MP4 decoders. So whatever your mobile has, your laptop has, all have decoders built in. Okay, so you can use MP4 decoder to decode it. Yeah.
So with this, we are coming to the end of this session. I will stop sharing. I will stop you as a presenter.
In the next session, I want 2 logins. So my colleague will be joining from his place. Okay, for the demo. So that is possible.
Please provide his or her email address to Akan Madam.
Okay. I already sent the link. Okay.
Okay.
So he will log in with the same link. Yeah.
Probably if you say email ID will be required something else that we require to approve also, I suppose.
Okay, I will send it. Okay.
Yeah. So please send it. We will surely add and then we'll approve also. I will send it to Sure.
Yeah. Thank you.
Thank you, sir.
Thank you, sir. Thank you, sir. It was a great and wonderful session from your side. We have learned so many things, how to develop the medical equipment and how you have developed medical equipment and products at ITIE Knowledge Solutions Bangalore that we have learned. The most important thing you insisted all of us to work on fundamentals. That is the important thing to carry out research in any field. So thank you so much for that, sir. You have talked about various parameters like frequencies, signals and systems, ADC, convolution and correlation algorithms, transforms, digital features. So we have learned all these things thoroughly and how these things can be applied if you want to carry out the research. That we have got an insight from your lecture. Sir, we also learned how medical image processing is carried out at your end at ITIE Knowledge Solutions. It was a great and wonderful opportunity for all of us to learn from industry person like you, sir. Thank you so much, sir. Thank you, sir. So, dear participants, we are going to start with another session at 2:15. Sir, we are going to start the second session at 2:15, sir.
Sure. Thank you.
Thank you, sir. Thank you so much.
Thank you, one and all.
Thanks. Sure.